Therefore, separating this into variables, we get x dv by dx equals 2 plus v by 1 plus 2v minus v, which on further simplification gives of this. Is what this equals this. Now clearly I can separate this into variables and then I get 1 plus 2v by 1 minus v square of dv is dx by x, which we're going to solve using the method. Now this on further simplification gives 1 by 1 minus v square dv minus 1 minus of integral minus 2v 1 minus v square dv is integral dx by x, which on further simplification, as I have adjusted this, splitting the term as 1 by 1 minus v square plus 2v by 1 minus v square, which is adjusted as minus of minus, because integral of f dash x by fx is log mod fx, and integral 1 by 1 minus x square is log mod a minus x by x plus x minus integral f dash x by fx, which is log mod 1 minus v square, that is equal to integral dx by x, which is log x plus c, is how we get each of logs expanded. So we have this as log of this equals this, which is eliminated with the log. That is, taking this inside 1 minus v whole square by 1 plus v whole square whole by 1 minus v square, which is 1 plus v 1 minus v, using the formula log a plus log b is log ab, and log a by b is log a minus log b, is what we get when we simplify through log. And this on simplification gets cancelled, and we get this as log x plus c. Then this is log 1 minus v 1 plus v whole cube is log x plus c. That is, taking this to the left, log of minus this as x times equals log c dash. That is, c is written as log c dash. That implies 1 minus v is c dash x of 1 plus v whole cube. That implies my x, which is x minus h, is written as x minus h, that is minus of minus 5 by 3 plus 5 by 3. So capital X is denoted by 5 plus 3. So I get this as 1 minus v y equals vx, implies v is y by x, and therefore I get this as 1 minus y by x equals c dash of x whole cube, which on further simplification gives x minus y as c dash x square of x plus y whole cube by x cube, where one of that gets cancelled, and hence we get x times of x minus y is c dash of x plus y whole cube, where x and y are replaced using the h and k. Therefore, I have my h and k through which I get x and x. My x, which is x minus h, and y, which is y minus k, from the original substitutions when substituted with h and k, gives capital X, which is x minus of minus 5 by 3, and my y, which is y minus k, are the two values which are substituted in the given function. Therefore, my x, which is x plus 5 by 3 times of capital X, which is x plus 5 by 3, minus capital Y, which is y minus 1 by 3, is minus y plus 1 by 3 is c dash times of x plus y, that is this plus this, x plus y plus 5 by 3 minus 1 by 3, which is 4 by 3 whole cube, is what we get. This, on further simplification, x plus 3x plus 5 by 3 times 3x minus 3y 2 plus 6 equals c dash of 3x plus 3y plus 4 whole cube by 3 cube. So this, when cancelled with this, 27 times 3x plus 5 of x minus y plus 2 is c dash of 3x plus 3y plus 4 whole cube, which I bring it here, and c dash by 27 is some other constant which I get here. Is taken as some constant k. Therefore, 3x plus 5 times x minus y plus 2 is some arbitrary constant k times 3x plus 3y plus 4 whole cube. This is how we get the solution of the non-homogeneous differential equation with case 2 as solved using variable separation method and the homogeneous method respectively. In this case, we use the homogeneity reduced to non-homogeneous function reduced to the homogeneous function using the concept of x equals x plus h and small y equals capital Y plus k, and then solving to give this answer. The limitations of non-homogeneous differential equation clearly makes us understand that if suppose the differential equation is in the form of this, only then I can use the method 3 either with case 1 or case 2, but any other non-homogeneous differential equation other than this cannot be applied with the method 3. So the clear limitation out here is that method 3 is applied only when the differential equation is of the form of as given in equation 1. Other than this, I cannot use if the right hand side has another homogeneous or other non-homogeneous differential equation. Non-homogeneous differential equation is restricted only to the form of the linear form by the linear form in the numerator and the denominator, is how it's limited. Now let's see the learning outcome of the method 3, that is solving of non-homogeneous differential equation both with case 1 and case 2. As we have seen the solving of non-homogeneous differential equation, we have seen that indirectly we have reduced that into the homogeneous form or using the variable separable method. So the case 1 always reduces the non-homogeneous differential equation into variables separation method, and case 2 reduces the given differential equation in reduces the given differential equation into homogeneous form. Hence, we use y equals vx is how we understand that the intention of case 2 of solving the non-homogeneous differential equation is to put an effort in reducing this into homogeneous form and then follow with the method 2 as we have seen, and this directly in substitution through variable separation method using substitutions. Case 1 involves substitutions, case 2 involves reduction to homogeneous form. Is how we get the learning outcome of in solving using the method 3, the solving of non-homogeneous differential equation with case 1 and case 2. The next is solving using the linear differential equation. But before that, let's see what exactly is a linear differential equation and hence see the method 4, which involves solving of linear differential equation. So what is a linear differential equation? A linear differential equation is a differential equation of the form d power ny by dx power n plus p1 d power n minus 1 by dx power n minus 1 plus p2 d power n minus 2y by dx power n minus 2, so on and so forth till p and y equals some r, is called a linear differential equation where is called a linear differential equation of degree 1 and order n, where p1, p2, p3, pn minus 1, pn are all constants or functions of x only. Therefore, a linear differential equation is a differential equation of the form d power ny by dx power n plus p1 of this, p2 of this, so on and so forth till pn of y equals r, which is called a linear differential equation of degree 1 and order n, because the dependent variable is always raised to power 1. As can be seen here, the order is n and the power of order is degree 1. And each of p1, p2, p3, pn, the coefficients of the derivatives in each term are either constants or functions of x only. No y term involved in the functions p1, p2 till pn, is how we define the linear differential equation in this case. For example, minus 3x squared d square y by dx squared plus 4y equals 7 is how we connect this with linear differential equation. So this is a linear differential equation of degree 1 and order 3 is how we understand the linear differential equation connected with the method 4. Now let's see in the method 4 exclusively in solving of linear differential equation of order 1 only. The higher orders are beyond the syllabus of the session. So in the restricted part of the syllabus, let's discuss about linear differential equation of order 1. So how do we define the linear differential equation of order 1 is how we're going to start with. As seen in the previous case with linear differential equation of order n, if n equals 1, then clearly the differential equation of the form of this is called a linear differential equation of order 1 because the order is 1 and degree is 1 for this differential equation, and hence this is called linear differential equation of order 1, and where PQ are either constants or they can be functions of x along is how we define a linear differential equation of order 1. Let's take an example problem of the similar linear differential equation. Suppose I have a differential equation in the form dy by dx plus 3x squared y equals x power 7. Then this clearly is a linear differential equation which can be compared to this, where here I have my p, which is 3x squared, and my q, which is this. Is how we understand a linear differential equation of order 1 with p equals 3x squared and q equals x power 7. Now next we see on how to solve the linear differential equation of order 1, which is method 4. Solving of linear differential equation of order 1. So let's see the method. So in this method of solving the linear differential equation of order 1, which is considered as dy by dx plus py equals q, then in this case we just multiply. The step 1 involves multiply e power integral p dx on both sides of 1. This is how we proceed with step 1, where we multiply both sides of equation 1 with this. Step 2, is integrating using the formula. So with these two steps we get the answer as 2y e power integral p dx is equal to integral q plus is how it gets reduced using the quantity e power integral p dx. So the solution of equation 1 is obtained by two steps, step 1 and step 2, with first step involving multiplying this on both sides of equation 1 and step 2 involving integrating using the respective formulae, and hence This reduces to the solution y e power integral p dx is equal to integral q e power integral p dx dx plus c is how we obtain the solution. And note, e power integral p dx or p of x dx is called the integrating factor of 1. We call this as integrating factor of 1 because this helps us in integrating the given differential equation, and hence this is the integrating factor of 1. Helps in integrating the given differential equation with its solution, this. Now let's discuss some related problems to understand the concept more better, that is solving of linear differential equation of order 1 with an example problem. So let's take an example problem where I need to solve the differential equation x dy by dx plus y times e power x equals e power 1 minus x of e power x. So in order to solve this, initially let's convert this into linear form, which is very important. Converting the given differential equation into the linear form is the first and foremost step. So I have to solve this by reducing this into linear form. So this differential equation, when remodified as dy by dx plus x e power x times y of x times e power 1 minus x e power x, is what we get when we simplify this, taking x on the right side, multiplying the whole equation by x. This reduces to the linear form, which is clearly 1 is a linear differential equation of order 1 in x, as we see here. That implies the integrating factor, which is denoted by I dot f, is clearly e power integral p dx, where I have my p is x e power x and my q is x times e power 1 minus x of e power x. So taking this integrating factor with p, which is x e power x, we get this in the form of this. Now integral x e power x dx using by parts is first integral second minus integral derivative of first into integral second dx is how we reduce this. Therefore, this is first function and second function. Using the IIB process, I get first function integral of second minus integral derivative of first integral of second, which gives integral e power x, which is this, which is x minus 1 e power x. Therefore, this by integration by parts gives x minus 1 times e power x. Therefore, this is the integrating factor. Now, this integrating factor using step 1 is to be multiplied to equation 1. Multiplying the integrating factor to 1, we get dy by dx plus x e power x y times this equals x e power 1 minus x e power x e power x minus 1 e power x, which is multiplied as the integrating factor to the right hand side of equation 1. Now this, when used with the formula, let's see how the formula is used out here. Now this integrating factor, when multiplied on both sides of equation 1, reduces to the formula. It's easy to remember the formula in this form, that is y times of integration factor is integral q times of this dx plus c, is how we get this. So let's see how the formula reduces to the given problem. Now y times of integration factor, which is e power x minus 1 of e power x, that is integral q, that is x times e power 1 minus x, this times integration factor, which is e power x minus 1 e power x dx plus c, is how this given problem reduces using this formula. Now further simplification gives y e power x minus 1 e power x is integral x dx, because these two get nullified. A power m times a power minus m is 1, is what we get. So using this, I get this in the form x dx. That implies y e power x minus 1 e power x is x squared by 2 plus c, is how we get this. To simplify this more further, 2y e power x minus 1 e power x is how we obtain the solution of the given differential equation using the integration factor formula, which is given by y times integration factor is integral q integration factor of dx plus c. So a linear differential equation of order 1 is solved using the integration factor e power integral p dx, and hence using the formula we get this. This is the solution of the given linear differential equation of order 1. Now when we come to the linear differential equation, we have classified with the respective method and the solution. We have two different forms which we're going to discuss in the session. Types of linear differential equation. Now suppose I take a linear differential equation in y and I take a linear differential equation in x, then they have their own respective definition, where in case of linear differential equation in y, it is dy by dx plus pxy equals qx. But if I take a linear differential equation in x, it is dx by dy plus p of y x equals q of y, is how we differentiate between the two linear forms in y and in x. If the dependent variable here is y, then it's called linear differential equation in y, and if the dependent variable is x, in this case we call that as linear differential equation in x. And in this case, the integrating factor is e power integral px dx, and in this case the integrating factor is e power integral py dy, and hence its solution is given by y times of integrating factor is equal to integral q of x of integration factor dx plus c. Whereas in this case, the solution of the linear differential equation x is given by x times of integration factor is integral of q of y integration factor dy plus c, is how we understand between the linear differential equation in y and in x. Solving of linear differential equation in x and y depends respectively with the respective formulae and the respective integration factors.